elastomer selection for biofuel requires a systems approach. Okay, that was the title of their paper. And the two scientists who, from Trelleborg Limited, who put this together, presented a paper in what I might call today's guest publication, Sealing Technology, which is a must-read, I'll tell you. Right, so what is the challenge? The challenge is that the use of biofuels presents a means, or the good side of it is it presents a means of reducing carbon emissions and also reducing the Western dependence on imported fuels, although in Britain I don't think we're going to be growing our own gross biofuels. However, the traditional and existing elastomers is a clever word for seal materials, are not really optimum for biofuels or larger biofuel mixes. Fatty acid methyl esters, FAME, not of the song type, FAME chemicals are chemically different to diesel distillates. They've got a different structure, and so you can get reaction. Anyone who has put the wrong hydraulic fluid in their brakes and seen their seals and everything go ballooning up will know all about this. I did it once. And the increased water absorption in biofuel can lead to an acid attack in the component that can actually break down. We think seals, they won't be subject to acid attack. Well, they can be. There are also, within the specification of these regulations, there are changes to the aromatic content, things like benzene. If you remember your chemistry back at school, you heard of the benzene chemicals, the ring hydrocarbons. They're called aromatics because they smell. And in our existing fuels, there's a certain level of aromatics, and that actually helps, because those aromatics cause the seals to swell and therefore fill the gap between the two joints, and it keeps the fuel in and the muck out. If you reduce the aromatics, then the swelling effect can be reduced, and therefore you can end up with weepage and leaks and so on. However, having spoken to various engine manufacturers, they're aware of this, and so they've been changing their seal materials over the years and looking into this along with these people to find seals that will do the job better. And the engine manufacturers that you'll be able to meet at the coffee breaks and at lunchtime will be able to talk to you in more detail about what they've been doing. Okay, but this is the challenge. Okay, right. The Trelleborg scientists identified that the traditional laboratory trials of materials can sometimes hide the effects of on elastomer performance. Okay, and what they said, funny old thing, we engineers might say, is that if you recreate the sorts of conditions that you'll find on the engine, you're much more likely to get a realistic trial of your sealing material. And that involves not just heat and pressure, but also water content. And that was the crucial difference of the work that these people did. And we'll see a little bit more of this. They covered in the article, they covered both compression ignition engines burning diesel fuel and spark ignition engines burning petrol, basically gasoline, with an ethanol, various grades of ethanol mix. I'm not going to cover that side of things because principally we're less interested in bioethanol than we are in biodiesel. Okay, so we've concentrated on that. And so on the diesel trials, they subjected 7 seal materials to heat pressure, chemical environment and water, typical of the seal locations found on the engine. Okay, and that's fairly crucial. I've mentioned that they considered the diesel and the ethanol. We're going to concentrate on diesel. And in their compression ignition engines, they use 2 fuels. Diesel fuel to EN 590, which I'm fairly sure I really need to talk to them, but I'm fairly sure that they had a 0 FAME content. It might be that it was actually an ultra low, but effectively it was virtually no sulfur. And then they put in their B30 test fuel, as they called it. They put a 30% biofuel content. That is pretty gross. I mean, that's a lot of biofuel. Okay, so 30%, a lot more than we would see in the sorts of fuels that we were talking about earlier. Now, here's where this is where you can take a snooze if you want to. These are the 7 different sealing materials. There's a fluorosilicon, which I sort of think of a bit like the stuff you use in your bathroom, or when you're building an engine and your gasket doesn't fit, you know, put some of that in. But this is a proper seal material with what they call a peroxide cure process, and the preference is these are ones that are identified for diesel connectors in your fuel system. Okay. Then there were fluorocarbon, these FKMs, basically fluorocarbons. Number 2 was a copolymer, so a full polymer chain with a 66% fluorine content. That's a lot of fluorine, isn't it? So it's basically carbon with the hydrogens replaced by fluorine. And this bisphenol cure, that's the way they cure the thing, okay? And that's okay for connections, not necessarily ideal. Then number 4 and 5 were terpolymers. That's where you've got chains of 3 with different fluorine contents, again bisphenol, and different, the number 4 ideal for diesel pumps, so higher pressure applications. Number 6 was tetrapolymer, so it's like 4 groups of 4 carbons. That's okay for diesel pumps. Number 7 was a tetrapolymer with a different fluorine content, and number 9 was a tetrapolymer as well, again with a different fluorine content. Note that the very minor changes to the fluorine content seems to have quite a change on its application. So that, you know, these guys are, I hope, clever. They know their stuff. Okay, what happened? Well, they were really looking for 4 different effects. The volumetric swell, i.e. as you immerse this stuff in the diesel and subject it to the pressure and temperature, the swell, how much it takes up the gap in your joints between your flanges. The change in tensile strength, i.e. so that it won't break under load as the whole thing's rattling around. The change in the hardness, if the seal is too soft, then it'll just get extruded out by the pressure of the fuel system. If it's too hard, then it'll tend to shear under the rattling around that it gets in a diesel engine. And then changes in elongation, necessary, important to keep the seals effective. And they then subjected the whole shebang to trials with the biodiesel fuel, and then with really quite a small additional amount of water in there, okay, to see what effect that had. And that was dissolved water, not free water, okay. So that's their trials. Now here's the interesting bit, okay. You'll notice the numbers there, the big numbers, those are the different seal materials, and it gives you some little key there. But the lighter line, let's see if we can get this to work. Here we go, there we go. These lines in the grey, they're the diesel. And these darker lines are the sealing material, this one or that one, okay? And so there's the sorry, the lighter lines are with the biodiesel for that sealing material. And it's really the difference in performance that we're examining, not the overall level, but the difference between that one and that one, and that one and that one and that one and that one, and so on. I think you'd agree with me that actually there's not much difference, and this is with a 30% biofuel mix. So in terms of volumetric swell, not much difference. Tensile strength, bit of a difference there, but proportionately not a lot, less than 10%. Same for elongation, that one's a bit dodgy, looks a bit dodgy to me. And in hardness, there are some changes over here, okay? But by and large, not going to spoil your day. Okay? That's not really a scientific term, is it? So the volumetric changes for the various compounds between normal diesel fuel and the 30% biodiesel, less than 10%. Not gonna, not gonna change your day. That's why, driving our old cars and trucks around, we haven't seen fuel leaking all over the place, or no more than normal. The tensile strength and hardnesses are reduced by extended exposure to the fuels, but the differential performance is less than 5%. So again, not too bad. So it all looks okay then, doesn't it? Well, then they started shoving a bit of water in, and all of a sudden, certain of the seal materials displayed very different characteristics in terms of volumetric swell, tensile strength. This one just fell apart, so they couldn't test it. It lost its strength. Okay. Hardness. There were some significant changes in hardness. This one broke. So the elongation. That one looked quite good because there's actually no change, although in the hardness there was quite a big change. Okay. So while with the biofuel, virtually no effect. As soon as that biofuel is contaminated with water, big effect. Okay, could end up with weeping, wailing, and gnashing of teeth. So there we are. Those are the results that identified some seal materials that are better than others, and this is really for the sealing specialists to talk to the engine manufacturers to make sure that the seals that are going into the engines and onto our fuel systems are really the best for the duty. Okay, and I'm sure our engine manufacturers are talking to them and getting the best results. Here's an illustration of what happened when the water was contaminated with fuel and then subjected to immersion under pressure for 366 hours, I think it was. That's the original size of the seal sample, and this is what happened to it. You'll see that this one has really sort of not too bad. This one, and this one have not only grown and lost their strength, but they're covered in blisters. This is just the sort of thing you see on your hydraulic system, on your brakes, if you put the wrong fluid in, and it leaks out and the brakes don't work. So these ones are going to be okay. This one will be okay in certain circumstances, but it did have some weakness. But these ones, not too good. Okay, and they come up with the reason for this is that when the water gets into these fatty acid methyl esters in the biofuel, hydrolysis, either the esters take in the water and there's a chemical reaction that goes on which ends up with carboxylic acid. I think I can remember that from the chemistry lessons, and that then attacks the seal materials and causes this. And the peroxide cured materials, that's these ones, were less effective than the bisphenol cured ones. So that's a bit of science for them and the engine manufacturers to have a look at. Okay, so the choice of seal materials requires careful testing under laboratory conditions, which should replicate the engine operations. The seal performance has been demonstrated as acceptable with a mix. Remember, it was 30%, so long as the fuel is kept clean and free of water. And it can be seriously degraded, so we could end up with more leaks, okay, if there's dissolved water in the fuel. Golden rule: keep your fuel systems clean and water free. Just a few acknowledgements. The clever people who put the article together, and Sally Becken from Knowledge Transfer Network, who had been trying to get the speaker for us. The full details of the report, if you want to look more into it, maybe the engine manufacturers would be interested, are in this, as I've said, today's guest publication, Sealing Technology. That's its registration number, and it was the January 2009 edition. Okay, that information is in your packs. There we go. Thank you very much.